let's talk about this one here, and then we're going to finish up for the day. What I'm going to be doing today is I'm going to be talking about what we missed out on last lesson. So when I say what we missed out on last lesson, I'm talking about what we didn't get a chance to do. So to explore what we didn't do, let's go backwards a sec to say, well, what did we do? Last lesson, we looked at lesson 7, displacement time graphs. Now, in displacement time graphs, what we did is we constructed a displacement time graph for this example here. And what we did is it looked like, and I'm going to do my best to try and recreate it, but it looks like this. Initially, the mouse went away. Then it, whoopsies, man, this is why I can't do it. Initially, the mouse went away at a steady speed because it was moving towards where the cheese was. Then it stopped and nibbled the cheese for a while. Then it moved back towards this hole. And then it sort of ran towards this hole really, really quickly. We actually had I drew a not much nicer curve on a piece of paper, and hopefully you guys did too. What we did was we talked about stuff. We said, hey, did you know we can measure the speed here if we find out how far did it go? So how far did it go in what amount of time? And we looked at the speeds of a couple of these things. Then what I did is I sort of talked to you guys about speed versus velocity. I said that velocity is just like speed, except it's got a direction. So we could say north, 10 meters per second north, or 10 meters per second forward, or 10 meters per second up. Any of those ways, as long as you've got a direction, you'll be fine. Or 20 meters per second at 30 degrees, one of those sort of ways from the horizontal. We went through delta, and this was literally as I was running out of time. I said delta means a change in something. So change in velocity, change in time. Delta x means a change in position. So we went through those, and then that was it. Today, I've only got one slide, I believe, to go through. Let me just double check. Yeah, now I've got 1.5 slides to go through, but the other one you don't have to copy down. What I would like you to do is I'd like you to draw a quick displacement time graph. When I say a quick displacement time graph, I am literally not expecting this to be super accurate. If you just go 3 centimeters up and 6 centimeters across, you should be fine. Don't have to draw these boxes in. The only reason that I want you guys to do that is so that you can plot in these 2 lines. And we're going to talk about what those 2 lines mean. Because the whole point of this lesson is to talk about gradient, we're going to discuss what these gradients mean. So I'm going to give you guys a little bit of time. I might give you guys a minute to do this because you guys are going to need a minute to probably get a displacement time graph. You may want to put units down. I'm going to make this top one displacement. I'm going to make it in meters. Maybe this bottom one we're going to put in seconds. So I'm going to give you guys a minute from now, and then I'm going to go through the rest of the slide. Okay, so first what we're going to do is we're going to discuss, well, what does the gradient mean? So the gradient is, of course, for those of you guys that don't remember, is rise or run. But the gradient of a displacement time graph is more than just the rise or run. The gradient is, The gradient is the rate of displacement changes over time. So it's how quickly is your position changing? Is your position changing very slowly, or is it changing very quickly? Now, if you've got an idea of how your position changes over time, what you can do is you can use that to create your position is going to be rise over run, because that's what when we talk about rate of change, when we talk about gradient, we're talking about rise over run. And your rise of a run is going to be, your rise is going to be displacement, and your run is going to be time. So what you're going to have is you're going to have your change in displacement over a change in time. How much have you risen by, which is how much your displacement has changed, over how much your run has gone. How much have you gone from left to right? So, and we know the displacement over time, or a change in displacement over the time, is the same as velocity, because we just talked about that in yesterday's class. If you remember, let me just flash back for a second. Velocity is we said a change in velocity is velocity happens to be a final velocity minus initial velocity. Velocity is also how fast you're moving. It is a change in velocity it's a change in displacement over time. So therefore, if you find out the gradient of a line, if you find out the gradient of a line, then that will give you your velocity. So, and that's what it says here. Gradient on a position time graph is the velocity. It's how fast you're moving. It's the rate of change of your displacement. Steeper lines means moving faster. And of course, what we'll do here is I will add an extra line for you guys down the bottom, which I'll say positive m or positive v, because we're talking about equals moving away. Just because this links to the attendance question we just did. Thomas, you just joined the class, welcome, but you need to make sure that you've done the attendance question by the end of this lesson, even if your internet's not that great. Whereas negative v means moving towards. So in this case, we've got a positive gradient. It's moving away. Let's look at this gradient actually. Let's look at this thing. If I take this gradient here, if I draw this, actually I should change to green, shouldn't I? Because I'm going to draw this green one. If I draw this triangle here, I have a rise of 6. I have a run of 6. So therefore my m, which is the same as my velocity, the gradient m, same as the velocity, is a rise of 6 over a run of 6 seconds. So that actually makes it positive 1 meters per second. And that actually gives me a velocity because I put a sign here. I put positive 1 here. So that's the speed that this is moving at, is at 1 meter per second. You can see that at after 1 second it's a 1, after 2 seconds it's a 2, after 3 seconds it's a 3, and so on and so forth. Now what we can also do is we can also do this other one in blue. So this one's also got a run of 6 seconds. We're going to do that here. M equals V equals a run of 6 seconds But this one only has a rise of 1, 2. So it only has a rise of +2. So if I do this, I actually get 1/3. It's still positive though. Positive 1/3 meters per second. So that means both of these are moving away, but this one is moving 3 times faster than this one. So that gives you a good idea, and they're both moving away because they're both positive. Their velocity, where is that? Let's read down the bottom here. They're both positive. They're both moving away. So that's what the gradient does. The gradient is a change in displacement over time, which is the same as velocity. What we're going to do next week is we're going to really explore this formula, the change in position over time. But I will tell you guys that even that basic formula is enough to do a lot of interesting mathematics too. And this is going to be the last slide I'm going to talk about, which is this slide here. Oh, I should have put those near far things in here, but this is another way that I can tell that it's moving away, is because I'm going from points that are very, very near to later on going to points that are far away. That's another way that I can confirm these types of things. GPS, no pencil here. You don't have to copy this down, but what I've tried to do is that every couple of lessons, I want to always touch base back towards engineering. It's one thing to go nuts and talk a lot of stuff about displacement and time graphs and stuff, which is really useful, but where's engineering? So GPS, flying above our head, is one of the greatest systems of all time. 24 satellites send out radio waves with their exact time. Now, I thought when we talk about modern technology, and we talk about being able to send information instantaneously, it's like when we're able to talk about being able to publish something so that everyone can read it in the world in literally half a second. That's really, really great. But one of the ones that I always really am the most excited about is GPS. The fact that it doesn't matter where you are in the world, anywhere in the world, you can pinpoint exactly where you are using a GPS system. And the fact that most of us, pretty much all of us, have this incredibly complex system on our phone is amazing. If you think about, have you ever thought about the fact that people on ships in the 1600s would have killed, would have sacrificed people just to know exactly where they were on a map? And we can just do that when we're lost at a supermarket. It's insane. How do they work? How they work is this. What they do is they don't send out their location, they send out their time. So if you send the pulse at 12 p.m., so what time is it now? 12:10. If you send a pulse at 12 p.m. from satellite A, and if you get that pulse, that 12 p.m. pulse from satellite A, before you get the 12 p.m. pulse from satellite B, you are closer to satellite A. So if you were sitting here at this point here and you get this, if you imagine that like the bell rings, a bell rings in town A at 12 p.m. and you hear the bell ringing in town A before you hear the bell ringing in town B, that bell ring has got a longer distance to travel. So therefore you must be close to satellite A. Now that's not enough to say exactly where you are. You need to have 3 satellites to pinpoint exactly where you are, because you need to have 3 overlapping circles. And I've also, technically what they do is you actually need 4 circles to get really high accuracy, but 3 will get you a general position. How it works? Well, the speed of light, so these are sending information at the speed of light. If you know how long it took you, so if it's 12 p.m. and it took 1 second, if you multiply C by 1, that will tell you your distance away from A. And if you do this with all 3 satellites, you can pinpoint your exact position. This formula here, x equals c times t, is just the same as saying v equals x over t. The only difference is I've moved the t to the other side. X equals vt. And instead of using v, I've used c because c is the speed of light. And that's why the clocks in satellites have to be exactly precise. Now, this is an engineering problem. What solution did this solve? What problem did this solution solve? It helped us do a lot of things. It helped us know the exact position of an object on the Earth. This was initially developed for military use, obviously, because it's really useful to know exactly where your troops are. But now the fact that we can use it to navigate, to drive, to pilot drones, to send, to locate packages, it's just, you know, what the world engineers, like, I've got to tip my hat off to you guys for GPS.